Hello, my name is Tim Pridemore, and I am the Environmental Compliance Officer here at the University of Tennessee, Chattanooga. The reason we're here today is to talk about lab safety for students. This is part of a broader program that's been put together and is being rolled out campus-wide to improve the already high level of safety that we have here on our campus. Throughout your career here at UTC, you're going to be exposed to a number of potentially hazardous environments. In doing that, we want to make sure that we keep you safe. It's important to recognize that safety is not something that's provided exclusively by the university. A safe learning or working environment depends upon each person meeting their responsibilities to create that environment. Regulations relating to safety typically come about because someone's injured or someone dies. It's important that you follow your faculty members' instructions at all times. The instructions your faculty member gives you are based on their experience, and they are designed to keep you safe. You must understand how to work safely before you enter the lab, use any equipment, or handle any materials. It's up to you to know what the safety protocols are. You must read and adhere to the safety procedures. We can't fix what we don't know about. For that reason, if there is a problem, you need to let us know. Notify your faculty member, notify your shop supervisor, or you can call the Office of Safety and Risk Management. We will do whatever we can to keep you safe and make sure that you graduate on time. Creating a safe working environment or a safe learning environment is a lot more than just a list of do's and don'ts. Our purpose in being here today is to look at a process that we can use to identify potential hazards, determine a relative level of risk, and come up with a plan to reduce that risk. In order to create a safe environment, we need to agree on an operational definition of the word safety. How would you answer the question, what is safety? Could you say safety is not having an accident? Would that be true? We all know that someone that does things that aren't quite safe, but always seems to get away with it. The absence of accidents does not mean that something is safe. It only means that the factors which cause an accident have not all come together at the same time and at the same place. An example would be if a car manufacturer sold a car that they knew had a defect which would cause that car to burst into flames if it were involved in a rear-end accident. This actually happened in the 1970s with the Ford Pinto, but no one knew that it was unsafe until the accidents began to happen. So the simple fact that the accidents had not happened yet did not make that particular vehicle safe. For our work today and throughout your academic career here at UTC, this is the definition we're going to use for safety. This definition includes determining the source of hazards, assigning a relative risk value, and developing a plan to reduce the level of risk. Notice it does not say the absence of hazards. Hazards are always present, nor does it say the elimination of risk. It's never possible to drive the risk to zero. But this is a good place to start. Let's consider the words of Scott Crossfield. Colonel Crossfield was in his own right an outstanding engineer and scientific researcher. During the 1950s and 60s, he led the X-15 high-altitude, high-speed research project for the United States government. Colonel Crossfield always told his team, there's no such thing as an accident. If something goes wrong, it's because we either designed something wrong, we built something wrong, or we used something wrong. Our goal in this program is to help you design, assemble, and conduct your experiments and your research and the demonstrations that you do so that nothing goes wrong. And if something does go wrong, that there are systems in place to prevent any actual harm. As we move through this presentation, we will be working to answer these questions. We want to do that within a framework which is replicable in your studies. The end objective is for you to bring you to a point where you can conduct your own safety analysis, your own hazard and risk analysis, and develop your own safety plan. So to start, let's answer these questions. The first question is, what is a hazard? There are many different definitions for what is a hazard. Some are more useful than others. For our purposes, the definition of a hazard is anything that can cause injury or death. Loss, in this case, can be monetary, class time, or anything that you would prefer not to lose. Hazards don't just happen. They all come from somewhere. And in the safety engineering field, another term for hazard is loss driver. Safety engineers often ask, what are the loss drivers? The environment includes all of the conditions under which you're working. The controlled environment of the lab or the shop is much different than the less controlled environment out on a job site somewhere. Both the lab and the workplace have their own unique set of hazards that you have to be aware of. Each of the things that you use, whether it's tools, chemical products, power sources, or anything else, brings specific hazards to your work. A cutting torch has a different set of hazards than a chop saw, even though the purpose of both is to cut metal. It's up to you to understand the hazards of what you're using both in the lab and later on in your working career. The things you do, the actual physical tasks or operations you're performing, also have their own sets of hazards. Understanding what happens during an operation, even one as simple as moving a glass container of hazardous materials from one part of a lab to another, helps you understand what can go wrong during that particular operation. We also have to understand the concept of risk. The concept of risk isn't complicated, at least not on the surface. When you hear someone say, I took a calculated risk, typically that's not true. The level of risk can be calculated, but there are some things that make it difficult to do so. First, it's not always easy to determine likelihood. Sometimes a hard number can be used. This would be the case in a situation where we know that some percentage of a particular piece of machinery is expected to fail before it reaches 1,000 hours of use. We can predict with a high degree of probability and accuracy when that's going to happen. But what about the probability that someone will drop a glass container while moving it from one part of the lab to a storage cabinet? In that case, we can say that it is higher, that the probability of someone dropping it is higher than the probability of it being broken because the building was struck by a tornado. But in either case, we can't really define or assign a numerical likelihood to that. Likewise, while we don't always know what the damaging effects of a particular event might be, we can say with relative certainty for others. For example, what would be the severity if the Titanic were to hit an iceberg at 23 knots? We all know what happened. But what would the severity have been, or what difference would it have made if the iceberg had been smaller, if it had been spotted earlier, or if the turn to starboard had been executed more quickly? Would it have made a difference? Very much so. So we can't always predict the likelihood, and we can't always predict the severity. There's a lot of factors that enter into those. You'll find in your career here at UTC and in your working career later on that when it comes to calculating risk, a lot of professional judgment is going to have to go into that. It's also important to note that likelihood and severity are two completely different concepts. In this example case, the potential of severity of being involved in an accident is identical. The worst case scenario in either one of these accidents you see here is the death of all 4 passengers in the vehicle. But which are you more likely to be involved in? Auto accidents are so common that a multiple fatality car crash that occurs in a small town in Iowa probably would not even be known about in Chattanooga. You'd never hear about it here. A light plane crash, however, would probably make the national news, even if only for a short period of time. And that's true because the light plane crash is unusual, not because it's actually more severe than a significant auto accident. Consequences, on the other hand, are measures of potential damage. In the example you see here, regardless of the likelihood, the potential damage caused by commercial explosives is much greater than the potential damage caused by consumer fireworks. The type of injuries is identical. Burns, amputations, hyperbaric trauma, which is trauma from being hit by the blast wave, they're all the same, but for energy production per unit of weight, commercial explosives can cause much more damage than consumer fireworks. So as you can see, the factors which increase or decrease the consequences, or if you prefer the level of damage, are completely independent of the likelihood of occurrence. Once you've determined the relative likelihood and the potential outcome of a list of potential hazards, you need a method for comparing one to the other. This is done using a matrix like the one you see here, which plots the 2 variables. As you can see, when the likelihood is very unlikely and the impact is negligible, the risk is considered to be low. If either variable rises, so do the risks. In some cases, you'll see these charts made with numbers instead of descriptive categories. That's a totally acceptable method. It does not matter which matrix chart you use to arrive at your final answer. What does matter is that you use the same chart to assess all of the hazards in your particular project. The information that you get from this process will allow you to focus your time and resources. Through your time here at UTC, one of the things that you will find is there's never enough time to complete everything that you want to complete. You'll always be under the gun. So using a matrix like this to determine what is and is not important from a safety standpoint should become second nature to you. Do you see why, in looking at this, most of the time when people say, I took a calculated risk, it's not true? What is true is, most of the time they took a guess and they got lucky. So now that we have a means for assessing the hazard and determining the relative level of risk for each of those, and for deciding which one we want to correct first, how do we use that information to develop a safety plan to improve the level of safety and give us a safe working or learning environment? There are at least 4 paths we can take to get to our safer working or learning environment. Transferring the risk means one of 2 things. Either we have the work done by someone with a superior skill set. For example, if we bring in a contractor to do specific work that we don't have the skills to do safely, or by providing insurance so that if something does go wrong, we at least do not have any monetary loss. Avoiding the risk essentially is deciding not to do the project. We need to recognize that there is always some level of risk, no matter what we do. If the risk is low enough and the benefits high enough, we often choose to accept the risk. For example, we accept the risk of being in an accident in order to drive to work or school because the risk is within acceptable limits and it's outweighed by the benefit that we gain. One of the reasons we consider the risk acceptable is that generally, even without realizing it, we do things that decrease that level of risk. We do things such as wearing our seat belts, obeying the speed limits, and not checking our email while we're driving. We want to look now at other ways that we might mitigate or reduce the level of risk. To have this discussion, we have to agree on some ground rules. We're going to assume that the project's going forward. We will have to mitigate the risk that exists within that project. For the moment, we're going to lay aside the possibility of transfer or avoidance, and we're going to focus solely on methods for reducing that level of risk. Managing the risk is generally a fairly straightforward process. It includes 6 steps intended to identify, assess, and control the hazards. What we want to do now is go through each of those and see how they fit together. The first step is to identify that list of hazards. This includes all the things you're going to use and all the things you're going to do during your project. Be broad when you put this list together. Don't be afraid to include things. The more inclusive it is, the more likely you are to detect potential hazards before they become a problem. Also, you want to include things whether you think the risk is high or low, because if you don't actually analyze it, you can't determine what the level of risk actually is. Next, you should make a list of all the steps involved in the project. Don't assume that a step isn't hazardous. Any physical activity necessary to perform your task should be included on your list. The next step is to develop a set of hazard statements. For each project, you're going to have at least one, and more than likely several, hazard statements. For example, mixing a test solution and using that solution to actually perform the test are 2 separate tasks that have to be done. The important concept is to have a statement which can be used to directly influence and help you manage the hazards and the level of risk during each step of your project. It's important to break your project down into its component parts. It's not possible to assess the entire project at once. Typically, a chronological breakdown is the easiest to use, but depending on the project, other breakdowns such as by component parts might be just as valid. Let's look at the 4 parts of a hazard statement in detail. The first piece of information you need is a list of everything that you're going to use in your project. This is these are all the parts of the environment that enter into your project. You saw some of these earlier when we were discussing risk. If there's something that concerns you, add it to the list. Your goal should be to make the list as broad as possible. Make this list of hazard sources as inclusive as you can make it be. Include everything you're going to use for each subsequent step, and doing so is critical to your success. You also saw an abbreviated list like this earlier as well. The same principle applies here, which applies to identifying hazard sources. It's important to identify all of the parts of the step. As a rule, each step is designed to accomplish one physical task. So there will only be one activity listed in that step. That may not always be the case though. For example, a step may require you to mix product A into solution B while solution B is being heated. In that case, heating and mixing are two activities, but they should both be included in the hazard statement for this particular step. A failure mode is nothing more than the answer to the question, what can go wrong with this? Again, there may be several things that can go wrong, and you need to identify as many of them as possible. So when you're making this list, again, for each step, as you identify the potential failure modes, make sure that you include everything that you think can go wrong. The minute you decided that that can't happen is exactly when, yes, that will happen. Finally, you need to document the potential outcomes. As you'll see later, this is the single most important element in this step, since this is the element which will drive your final choice of control modes. Here we see a multitude of potential replies to each part of the hazard statement question. While this is not intended to be an exhaustive list, it gives you an idea of what you might consider. It's also, it's almost possible to choose one from each of these categories and put them together into a hazard statement. For example, you could almost say, we're going to be using a hot plate to heat samples of the test product. During that process, it's possible that we can overpressurize the vessel, which could result in an explosion. These are the four parts that make up the hazard statement. Also, it's not necessary to develop a matrix like the one that you see here. This is only being used to show you how the parts are related together. Here's another example of a complete hazard statement. Let's break this one down to see if we managed to get all four parts included in this. Here's where we see the source of the hazard. In this case, we know that sulfuric acid is very corrosive to skin tissue. Here we see information on what you're going to be doing. This is also known as the hazardous activity component. It's important to understand what can go wrong. This failure mode component gives us that information. It'll also be used later to help develop your control plan. Finally, we look at the specific outcomes. This is the how it can hurt you part, and it's also used to help you develop your control measures. We can take that hazard statement and we can put it into a matrix that looks like this one. At this point, we have the first step for the first hazard completed. From a process standpoint, what you need to do now is to continue down your list of potential hazards and develop all of the hazard statements before you do anything else. Developing the hazard statements first is important because the next step is to assess the relative level of hazard. You can't compare one hazard to another unless you know what all of the hazards are. So this part of the process will help you understand which project steps represent the greatest potential injury for causing, the greatest potential for causing injury or damage, and that information is used to help you decide where to focus your resources. You'll find that once you leave the academic environment and get out in the world of work, that this will be an extremely important issue because there are never enough resources to go around. With that said, it's important to note that you will complete the next step regardless of the outcome of the assessment. In other words, you'll develop a work plan and choose a control method for all the hazards you've identified, even if we don't use that information later on. When it comes to developing the work plan, it's done through the same process used to develop the hazard statement. The elements are different, but the process is the same. Using a list, you should be able to go through each hazard. Here's an example of a completed work plan which applies to a single step during the process. Let's look at it and make sure that we got all four components. The first thing you see is who's going to be doing the work. This may be an individual, it may be a group, or it may be some other subgroup of an entire larger team. The choice is entirely yours. At least in the beginning, your faculty members are going to tell you what the answer to this is going to be. You may be assigned to a team, you may be assigned to do this individually, so just pay attention to that information and execute accordingly. This is the part that lists all the equipment and materials used for a specific step. Make sure that this list is complete. We also see a statement telling us what needs to be done and, more importantly, how that's going to be done. Here we see where the work will take place. This may seem like a lot to remember, but if you're asked to write a safety plan in a workplace, knowing this process will help you be successful. Also, these steps are included in your student handout. So for the large part, it's going to be simply a matter of going back and following the steps, determining what the appropriate information is and plugging it into the right place. Once we get that work plan plugged into the right place, it's just a matter of moving on to the next step, which is to choose our control measures. Administrative control measures are those which help control our work through checks and balances or provide us with information on hazards. Prohibition against ordering specific chemicals, for example, providing lab safety signage, or prohibiting certain practices are all examples of administrative control measures. Anything which can change the actual environment is considered to be an engineering control measure. These are things like providing emergency shutoffs, installing guards on equipment, and taking steps to improve ventilation in a lab. Finally, work practices such as the use of personal protective equipment or using lockout-tagout systems have to be considered. These human element programs are highly dependent on attitude for success. If you or your coworkers don't have a safety attitude, problems will result. This is why you hear us say, if you don't make safety a habit, you are heading for an accident. So once this has been added to your safety plan, you've completed one step. Just repeat this process over and over until you've worked out a work plan for all of the hazards that you have identified. So here we see a part of a completed project safety plan. It contains all the steps, the work plans, the control measures for each step. If you complete this process and produce this document, you should be well on your way to having a much safer learning environment. The reason for that is knowing what the problems are and how you're going to either avoid or control them is what generates the safe environment that you need to work in. The safety plan tells us how to prevent accidents and minimize the damage from those that do occur. It's important to note this is not an emergency response plan. This does not provide you information on what to do if something does go wrong. That information comes under a completely different set of learning objectives. Your professor will give you specific instructions on handling problems in the lab or in the shop. Pay very close attention to what your professor tells you about what you should do in the case that something does go wrong. We hope the information we've given you so far has given you a better understanding of the hazard identification and risk assessment process. Using this and the information in your handout, you'll be able to write your own safety plans for the projects you're working on. You should note that in some cases, your professor may ask for copies of those safety plans as part of your deliverables for a grade. The next thing we want to talk about is topics specific to the UTC campus. We're working hard here to push the risk to students, faculty, and our staff members as low as possible. To do that in the academic environment, we've implemented several new programs to help identify hazards, reconfigure lab systems where we need to, require specific work practices, and to give you information that you need in order to protect your safety. As you know, these examples are of engineering practices, administrative practices, and work control measures. We want to have a complete program to make sure that you have a safe environment during your career here. What we want to do now is we want to look at what some of those practices controls we recently put into place is the addition of signage to provide you with more information on potential hazards in your labs. This particular one happens to be installed in engineering, math, and computer science, and it is, as you can see, specific to Lab 114 where the Mini-Baja project takes place. Let's take a closer look at this and at the information that it contains. In the left-hand column, you see several symbols. These give you a quick look at the hazards that are present in the lab. The first of these tells you that irritants are present. It does not tell you specifically what products are present. The flaming ball indicates the presence of oxidizers. Some oxidizers are relatively mild, pool treatment chemicals, for example, but some are highly reactive. Organic peroxides are notoriously unstable. Remember, the purpose of these gifts is to alert you to the presence of something in that category. It's up to you to find out what that problem might be. It's your responsibility to learn the safe way to handle, use, and store that product. We all know the skull and crossbones means poison. The principle that the gift alerts you to the presence of something and you're responsible to know what that something is applies here and across the board. That gift tells you that poisons are present, toxins are present, but it does not tell you what they are. The last gift you see here alerts you to the presence of something that can cause long-term and serious health effects. The gift labels are part of the global harmonization system. The purpose of this system is to provide information to anyone, anywhere, regardless of language barriers. In today's global economy, it's a necessary part of doing business. When you leave the university and start your career, you will see these there as well. These are the basic set of gifts to alert you to the presence of something which falls within one of these 9 categories. If you'll be handling chemical products, such as in chemistry, biology, or even in engineering, you may be required to take additional safety training which focuses primarily on the hazards of identifying, handling, and using specific chemical products. The second column contains general information specific to that particular lab or shop. You should read this information since it provides you a better understanding of the work practices expected in that lab. The third column gives you information about what's in the lab that can hurt you. This might be equipment, it may be saws, it may be high voltage equipment, it may be chemicals, it may identify biological hazards, or any of a number of specific hazards. This area can also be used to give you information on specific mechanisms for potential injury, such as pinch points or potential projectile hazards. The fourth column gives you the minimum, repeat, minimum personal protective equipment. These are the requirements for working in the lab regardless of what operation you're doing. I must stress that this sign provides the minimum level, and depending on the operation, additional personal protective equipment may be required. Follow your professor's guidance on the need for additional personal protective equipment. The last column gives you a quick visual reference for the minimum PPE. Again, I have to stress this is the minimum, and if you think you need additional protection, by all means, obtain whatever it is you need. It's also your responsibility to know your safety equipment. Take a moment to look at this picture and think about what you see here. And more importantly, what do you not see? What's missing from this particular collection? You should also know the location of emergency shutoffs and fire alarm pull stations. And of course, there may come a time when the best plan of action is enthusiastic implementation of the evacuation plan. For that reason, you need to know where the exits are. Open lab policies are intended to provide you with guidance for students who are working in labs when no faculty member is present. The key variation from college to college and department to department is who's allowed to work under these rules. For example, undergraduate engineering students are allowed to work under those rules if they're working on a specific project such as Baja Buggy. In the chemistry department, undergraduate students are typically not permitted to work in laboratories alone, while graduate students are. One of the most important parts of this is the prohibition against working in labs alone. This comes from an incident which happened at UCLA where a student was killed one evening 2 weeks before graduation, and nobody found her body until the next day. Remember when we said earlier that behind every good safety regulation, there's at least one dead body? That's where these regulations come from. We're not trying to frighten you, but we are trying to tell you what the realities of the world are. The open lab policy also sets access control requirements. When going into a lab, each individual must swipe their MOX card and sign the logbook. If somebody else swipes their card to open the door for you, that's fine, but you must swipe your MOX card when you go into the lab. Only a faculty member can authorize visitors to any shop or any lab. The no food or drink rule is intended to prevent possible contamination through ingestion. This is important in all labs, including and especially labs where biological hazards are present, such as in biology or in nursing labs. A chemical hygiene plan establishes procedures for the procurement, intake, storage, use, and disposal of laboratory chemicals. The prohibition against bringing in non-approved materials applies not only to students but to faculty members as well. If you need to use product which is not already in the lab, you must, without exception, contact the chemical hygiene officer for your department and coordinate the purchase through them. More information on this procedure is available if you take the Hazardous Materials Training Program appropriate to your position. When using chemicals in a lab or shop setting, they must always be in proper containers, properly marked and closed unless in use. There are no exceptions to this rule. Let me repeat that. If you are using hazardous materials in a lab or shop setting, they must always be in proper containers which are properly marked and which are closed unless actually in use, and there are no exceptions to that rule. With the information you've gotten here today, you should be able to perform a risk analysis and document your results. You should be able to produce a safety plan for your project or your shop work. Again, your professor may ask that you turn that in as part of your grade. Look at it this way. If you can identify the things that can hurt you and document how you plan to prevent that, then you get an easy grade simply by staying out of the emergency department. Also, your professor may have other specific things they want to see or other methods for performing the analysis and planning. Pay attention to their instructions since A, they're more familiar with the exact nature of the work you're going to be performing than I am. They can give you the view from closer to the ground much better. And B, having more than one way of reaching your objective of creating a safe learning or working environment is always a good thing. Finally, whether you're here at UTC or whether you're out in your career, always remember, good science is safe science.